Okay, good morning, everyone. Hope you had a good weekend. Today, we're going to be talking about tangent planes. So this is the last section of new material before the midterm. So you've got a midterm this Friday. I'll send out an announcement in the next couple of days detailing what to do on Friday. Wednesday is going to be a review session. So we're going to go back across all the topics that we've talked about over the last few weeks and go through some problems related to those, the kinds of things that you might be expected to do on the midterm. So that will be Wednesday. So this will be the last section of new material until then. There's also no instructor questions set for this week because of the midterm. Okay, so can I just have a show of hands who's already seen the pre-recorded material? Very good. Good to see that. Okay, so we're going to talk about what tangent planes are, slightly abstract to start with, and then we're going to be talking about something called linear approximations. So why do we care about tangent planes? Well, they allow us to do simpler approximations of complex functions that have multiple variables. So first of all, what is a tangent plane? Well, if we imagine we've got some surface that's maybe described by either an algebraic function of multiple variables or a table of values, we can think about a point on that surface, and in one dimension, we would just draw a tangent line to a curve. But we can't do that in 2 dimensions. We have to do a surface. So we have to have a tangent plane to our surface, okay, at a particular point. So you can think about this as being some wavy surface, and you put a flat piece of paper on the surface at a particular point. Okay, so how do we describe that plane? And it turns out we can describe it using something called a normal vector. So a normal vector is a vector that is perpendicular to that plane and some point that that plane passes through. Okay, so how do we do that? If we imagine some point that our tangent plane goes through, P, given by x0, y0, z0, and we think of some normal vector with components A, B, and C, then first of all, any vector within that plane we can describe as its initial point being P and its terminal point being some point with x, y, and z coordinates. Okay, so the components of the vector from the initial point P to wherever we want to go in that plane is going to have components x0, y0, and z0. And because our normal vector is perpendicular to any vector in that plane, it's going to have an angle of 90 degrees, which means that if we do the dot product between our normal vector and any vector in the plane, it's going to have it's going to be 0. It's going to be the dot product. So if we work that out, if we do ABC dotted with our vector V, then we end up with this equation for the plane, and that's true in general. Okay, we can also do a rearrangement of that. So if we take this A times by the X bits, B times by the Y bits, and C times by the Z bits is equal to 0, and we take the A and B parts over to the other side, divide throughout by C, then we end up with a minus A over C and a minus B over C as our coefficients in front of the X and the Y terms. And then because A and C are just some constants, we can say let A over C or minus A over C equal little a and minus B over C equal little b. And it turns out that little a and little b are given by our partial derivatives of our function at our point of interest, x0, y0. Okay, so we can work out our tangent plane by working out our partial derivatives, which we talked about last time. Okay, so this is an example of how we would do that. So we've got some function here, z is equal to some combination of x's and y's. We call that our function f of x, y. We first of all work out our partial derivatives, f subscript x and f subscript y. And we want to know the tangent plane to this surface at a particular point, 1, minus 1, 1. So then all we do is we substitute in the x and y values into our partial derivatives. So we end up with a -1 for our partial derivative with respect to x, and 2 for our partial derivative with respect to y. And then we use that equation from the previous slide, our z minus z naught And then we end up with an equation down here at the bottom. Z is equal to minus x plus 2y plus, sorry, minus 2y plus 4. That was plus 2y, sorry. Z is equal to minus x plus 2y plus 4. That gives us our equation of our plane. Okay, so that's all we would need to do. Sometimes it might be preferable to leave it in the z minus z naught form. We'll talk about that a little bit later on with linear approximations. So before we can do a linear approximation, we need to do something called a linearization. And all this is saying that if we have some function that has continuous partial derivatives at some point, then we can approximate that function, even if it's some really horrible nonlinear function. If we're close to that point, we can approximate it using our tangent plane. That's all this is saying, okay? So the reason being, if you think about this in one dimensions, first of all, if we've got some curve, then you can find a point on that curve. At a particular point on that curve, we can work out its tangent. And if you zoom in close enough, then anything that's curved starts to look linear. Okay, so if you want to work out your function value a little bit away from that point, you could plug in those values into your function, but that might be really computationally intensive. It might be difficult to do. There might be a variety of reasons why you might not necessarily be able to do that. Or you could just use your linear approximation and get a roughly good example, good answer for what you want. When we're in 2 dimensions or more dimensions, now we don't just have a tangent curve, we'd have a tangent surface when we have 2 variables. So now we can do exactly the same as before. Rather than having a tangent line, though, we have a tangent surface, and we can use that surface to approximate what is going on in our function. Okay, so we do that by setting our linearization. So this L of xy is our function evaluated at a particular point. So the point here is AB. So x is equal to A, y is equal to B. So that's our equivalent to our z naught that we had in the previous slides. And we add this to our partial derivative of our function in the x direction, evaluated at AB, times by x minus A, and then do exactly the same in the y direction. So this equation here, all it is taking exactly what we had here, okay? We're just evaluating this at some particular point, AB. So that's our linearization. And then if we want to make a linear approximation to our function f, we can say that our f of xy close to AB is just approximately equal to L of xy. So what we're then doing is substituting in the equation that we had for our linearization, substitute in our particular values, and then that will give us an approximate answer. Okay, so in this example, it's gone through in the lecture notes. We've got some function here, z is equal to 2x cubed plus 2y cubed minus 9xy. We want to approximate this close to the point 1, 2, and use that to find the value of z, our function, when x is equal to 1.06 and y is equal to 1.97, so just a little bit away from that. Of course, you could just chuck those values into the function. This is a very simple example, and if you've got a calculator in front of you, you could just do that, right? You might not have a calculator in front of you, so you might not necessarily be able to do that, or it might be much more complicated, okay? So we go through the process of creating linearization, just described, and then work out our linear approximation. Here you end up with minus 1.17, and the actual value is minus 1.12. Okay, so if we're fairly close by, the approximation is pretty good. If we had, say, picked x value equal to 2 and y is equal to minus 5, that's quite far away. It's probable that our approximation is not going to be very good. So these approximations only hold when you're close by. Yeah.
How do you find the actual value?
The actual value, as in this one in the bottom here, that was just substituting the x and y values here into this equation. That's okay. Any other questions on anything I've described so far? Okay, let's work through some problems then. I don't think there was anything else. Oh, only to say that we can do exactly the same thing in more than 2 dimensions. Okay, so we've worked this out in, we have a linear approximation in 1 dimension, 2 dimensions, 3 dimensions, and so on. It's exactly the same process. Okay, let's go through some problems. Okay, so this first one here, we want to find the equation of a plane that passes through point 1, 2, minus 1 and has a normal vector n is equal to 1, 3, 2. And then we want to see, is this point 0, 3, minus 2 on the plane, and how about some other point? Okay, so how do we do this? Well, we have a normal vector and we know a point that our tangent plane passes through. So if we go back to the lecture slides a second, we are in this kind of scenario here given by this diagram. So we have some normal vector and it goes through a point, and this will help us describe our tangent plane. And because we know that our normal vector is perpendicular to any vector in the plane, that means that we can take the dot product of these things. So we take the dot product of our normal vector, n, dotted with any vector in the plane. Okay, so if our point in the plane is given by x, y, z, and we know our initial point is 1, 2, minus 1, then the components of any vector in the plane is going to be x minus the x component of that point, y minus the y component, and z minus the z component. And this has got to be equal to 0. So this vector here, you just work this out by taking any point in the plane x, y, z, and taking subtracting the initial point 1, 2, minus 1. That would give you the components of any vector in that plane. So n dotted with this is equal to 0. So have a go at working that out, and let's see what you end up with. Okay, so if we want to take the dot product of these things, let's just substitute in n to start with, 1, 3, 2, dotted with x minus 1, y minus 2, z minus 1, so z plus 1. That's going to equal 0. Can anyone remind me how we do the dot product? Yeah? Yep, okay, great. Yep, so we take the components from one vector, multiply them by the corresponding components of the other vector, and then add those together. So in this case, we have 1 times by x minus 1 plus 3 times by y minus 2 plus 2 times by z plus 1 is equal to 0. Can anyone tell me what that ends up equaling? Yeah.
X plus 3y plus 2z minus 5.
Yeah, so I'm going to take the 5 over the other side, but that's exactly right, yeah. So x plus 3y plus 2z is equal to 5. Okay, so then we're asked to check whether this point 0, 3, minus 2 is on the plane. How do you think we're going to do this? Yep.
Just plug it in and see if it equals 5.
Perfect. Okay, so let's plug this in. So let's do check about 0, 3, minus 2. So x is 0 plus 3 times by the y component, which is 3, plus 2 times the z component, which is minus 2. So you have 0 plus 3 times 3, which is 9, and then minus 4, which is just equal to 5. This is in the plane. Okay, how about this point here, 1, 1, 1? Have a go at doing that and checking if that is in the plane. Okay, so if we sub this in, x is 1 plus 3 times by y, which is also 1, plus 2 times by z, also 1, which is equal to what? 6. Is it in the plane? Okay. Great. Does anyone have any questions about how we constructed that plane? Okay, good. Excellent. So find the tangent plane to this graph. Z is equal to 2x squared plus y squared at the point 1, 1, 3. Okay. So what you first want to do is let f of x, y equal this function 2x squared plus y squared. Can anyone tell me what is the first thing, or what is one of the next steps we can take? There's a couple of different routes you can start this by. What do we want to do? Yeah. Okay, yeah, so you want to find your partial derivatives. Okay, find what they are in general. Okay. And then once you've found them, then what do you want to do? Sub in your values. So you can have some value for f at 1, 1, fx at 1, 1, and fy at 1, 1. Okay. Have a go at working through those. Okay, let's work through this together then. So everyone just shout out, what is the partial with respect to x, just in general? 4x. Partial with y? 2y. Our function evaluated at 1, 1. Three. Our partial with respect to x at 1, 1. Or partial with y respect to 1, 1. Okay, so how do we write down our tangent plane? So z is going to equal what? It's going to be our function at 1, 1. This could have been on the other side. This is our z naught, right? This f of 1, 1. That could have been on the other side, but we can also just put it on the right-hand side here. So our function at 1, 1 plus what? Is that our partial with respect to x? Yeah. At 1, 1 times by what? I can hear but can't see where that was from. Someone over here? Was it over here? I heard someone mumble something. No? What do we multiply the partial derivative of f by? X minus 1. Okay, good. And then what goes next? Yeah, partial derivative with respect to y at 1, 1 times by what? Y minus 1. Okay, good. So if you evaluate this, okay, so substitute in all of those values that we had before. So 3 plus 4 times by x minus 1 plus 2 times by y minus 1. And you can simplify that further to 4x plus 2y minus 3. Okay, so if you're just writing down a tangent plane like this, it's good to write it in its simplest form. Z is equal to 4x plus 2y minus 3. But when we go into linear approximations, it's generally best to keep it in this earlier form here. The reason being is that when we're doing a linear approximation, we're starting at this point, which gives us a function value of 3, and then we're moving a little bit away from it. By definition, that means that the x and the y are going to be very close to whatever the point is here. So the bits in the brackets, the x minus 1 and the y minus 1 in our linear approximation are going to be very small. So we usually would leave it in this form underlined in green as opposed to going into the form underlined by blue, okay? So if you're doing a linear approximation, it's fine to leave it in this form given by the green line. If you're just asked what the tangent plane is, then go through to the blue form, okay? Okay, so we can also check that our point 113 is actually on this plane. And we do that just by substituting it in. So let's just check that that is definitely correct. So check that 113 lies on this plane. So we're going to have 4 times by 1 plus 2 times by 1 minus 3, which is 4, plus 2, which is 6, minus 3, which is 3. And that's our z value that we had all the way up here. Okay, so this matches that. So it's definitely in the plane. Okay, let's talk about a real world example that we don't have a function for, okay? So we've talked about various tables of values like this before. This is the heat index, I, and it's your perceived temperature when the actual temperature is T degrees Fahrenheit in this case, and the relative humidity is H, measured as a percentage. So I is some function f of T and H. We're asked here to find the linear approximation for the heat index when T is near 96 degrees and H is near 70%, and then use it to estimate some nearby values. So first of all, let's find, we're told we want to be near 96, T is near 96 degrees Fahrenheit, and H is near, should be a little h, I believe, should do a little h. This a little h as well. H is near 70%. Okay. So we want to make a linear approximation to our function somewhere near here. Note that this linear approximation here that we make is probably not going to be a good linear approximation over here or over here. Okay. The linear approximation that we make is only good at that point, near that point. Okay, so if we were just varying, say we just wanted to move in one direction, say we just wanted to work out what happens if we are close to, if we keep the same temperature or we keep the same humidity and we just move in one direction, we could just look at the partials. But if we want to vary both of those things, then we need to think about the tangent plane to get our two-dimensional linearization, okay? So we can take similar steps to what we did above. Remember when we wanted to approximate the partials here in a table like this, what we did is look at the next available point and say, okay, well, moving in the t direction, if we increase temperature, our partial of our function with respect to temperature is going to be approximately equal to, let's say this is ft at 96.70, so it's at a particular point. This is going to be approximately equal to our function value at the next step. So in this case, it's 133 minus what we started with, which was 125, divided by the difference in the input. So 98 minus 96. Okay, so we're just approximating our partial derivative by moving onto the next row in the table in this case, finding the difference in those values, in the output values, dividing them by the difference in the t values. Okay, so this works out to be, let's see, we can have 8 on the top and 2 on the bottom. So this is going to be 4. And then to work out our partial in the other direction, well, why don't you guys have a go at that? So work out the partial at this point in the direction of humidity. Okay, what do I write here for my partial? How do I work it out? $130 minus 125, so we take the next value along, minus the previous value, 125, and then divide it by what? 75 minus 70. Okay, good. So we're going to have 5 on the top, 5 on the bottom. So it's just going to be 1. Okay, so we want to work out our linearization at this point of our function. So our linearization at 96.70. So when t is 96 and h is 70. Let's call this a new function, capital L of t and h. It's going to equal, well, what are we doing here? We've got some nonlinear surface. We're making a linear approximation, so we're doing a tangent plane at that point. So we take our function value at that point. So our function value at 96.70, add on our approximations to the partial derivative, times by, in this case, t minus that point. So we're starting with a temperature of 96. We do t minus 96 plus, same in the humidity direction. So our partial derivative approximation with respect to humidity at 96.70 times by h minus 70. Okay, that's all our linear approximation is here. Does anyone have any questions about where that came from? Oh, okay, good. Okay, so shout out, tell me what I need to write down. What's our function at 9670? 125. You guys have lost your voices this morning. Enunciate. 125, thank you. Plus what? Yeah. Times by t minus 96. Plus what? 1 times by h minus 70. Okay. Now, because we're doing a linear approximation, we could just leave it in this form. You could also write it out as 189 plus 40 plus h. Both are correct. There's nothing wrong with doing that. But we'll see in a moment when it comes to working out these estimates that it's easier to work with the first one than it is to work with the second one. Okay. So we want to use this linear approximation to estimate what our function is, what our heat index is at some values close to that. So rather than being at 9670, we're going to move along to 9772 to start with. So we can say that our function at 9772 is approximately equal to our linearization that we've taken at 9670, but evaluated at 9772. Okay. So what's that equal to? Okay, well, we have our 125 plus 4 times by t values. So we're going to have 97 minus 96 plus 1 times by our h value, which is 72 minus 70. 125 plus 4 times by 1 plus 2. So we end up with just 131. So you see why this is sometimes easier to work in this format here, where we leave the t minus 96 and the h minus 70 rather than, so why it's easier to work with this one here rather than working with what we have in this blue circled box here. Because when we substitute our values in, the values in our brackets here are going to be very small. And we want them to be small because we're doing a linear approximation close to that point, right? So these should always be quite small. So it's easier to, in this case, just take our function value and then add or subtract a small amount to it, rather than here, if we had 189, then we need to work out 4 times whatever the temperature was. So if you're doing this in your head, you'd be working out 4 times by, let's see, you'd have 4 times by t was 97, blah, 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 and so on. So is this right? This 189, that doesn't look right to me now. This, I think, is wrong, actually. That isn't actually what the expression should be. Whatever it would have ended up being, that would have been a more complicated way to do it, because we would have had the 4 times by our temperature, which would have been working out what 4 times by 97 is in your head. And I'm not going to do that here. Obviously, it's actually not that hard. It's 389 or 88. I'm not very good at mental arithmetic, as you might have guessed. Anyway, it's generally easier to work with that form. That's the point I want you to take away. Okay, have a go at working out a linear approximation where when we have t is 97 and h is 69. Okay, so you're going to work out what is our function value approximately at 97.69 using the same process. Okay, so we've got our linearization at the point 9670, and we want to work out what our function value is approximately at 9769. So we substitute these values in. So we have 125 plus 4 times by the difference in the temperatures. So 97 minus 96 again, plus the difference in our humidity. So 69 minus 70. So now we're going to have 125 plus 4 minus 1. So 125 plus 4 minus 1, so just 128. I corrected this value up here, so if in blue, that should have been minus 329. That's a mistake. Okay, does anyone have any questions about how we take a table of values like this and then use it to make a linear approximation? Okay, let's go on to the final problem for today. Okay, so we've been working on functions with 2 variables, but exactly the same process applies if we have a function of more than 2 variables. So we can do a linear approximation to a function with any number of variables by doing exactly the same process we've done before. So here you've got a function of 3 variables. W is some function of x, y, and z. And we're told what the function value is at the point 121 and what the partials are with respect to x, y, and z at that point. And then we're asked to use it to use a linear approximation to work out what our function value is nearby. Okay, have a go at that, and I will walk around and see if anyone has any other questions. Okay, let's finish up by going through this. So we want to work out our function at these values 0.98, 1.97, 1.04. I mean, one of the first things we should do here is we should check that this point is actually close to our function values, okay? So this 0.98 is close to 1, 1.97 is close to 2, 1.04 is close to 1. So we can say that our approximation is probably going to be quite good, okay? If these values were much further away, then maybe we would say, okay, what's our confidence in our approximation? We could still do that approximation, but we maybe say, well, we're not very confident that it's going to be very good, okay? So this is going to be approximately equal to, because we can't write down exactly what our derivatives are. We can't write down our L of x, y, z in this case, our linearization, but we can just use the values that we've been given, the numerical values, okay? So we take our function at 1, 2, 1, and then add on our partial at that same point, times by the deviation, so 0.98 minus 1 in the x direction. Do exactly the same in the y direction. And in the z direction as well. Okay, and then if you evaluate all of that, you should end up with 13 plus minus 4 times by minus 0.02 plus 2 times by minus 0.03 plus 3 times by 0.04. What do you end up with? 13.14, good. At least that's the answer I came up with. So either we're both wrong and we're both wrong in the same way, or hopefully everyone else got the same thing. Okay. So someone asked a really good question about, you know, if we can just substitute the values in to our function like we had on the previous example, sorry, the example earlier on, 11.2 or wherever. Why don't we just do that? Why don't we just substitute these values in? The reason that you're being taught these techniques is because these techniques can be applied to problems with many, many variables and when things are very, very complicated. Unfortunately, we can only give you guys very simple examples to test your ability to understand the concepts of how we construct these things. I can't give you a function with 1,000 variables, or I hope, you know, I don't think you would want me to give you a function of 1,000 variables and work out what the linear approximation is to that. But you would use exactly that same process if you were doing this in the real world, okay? So some of these examples you say, well, why bother approximating it if we just have this function here? Well, one reason is because of the same concepts are applied in the real world with much more complicated examples. Also, if we have something like this, a table of values, you have to make these approximations if you want to move in a diagonal direction, okay? So you could make a one-dimensional linear approximation by just looking at the partial derivatives going in one direction, but if you wanted to go diagonally and essentially interpolate across this table, suppose they were a little bit more spread out, you wanted to have a fairly good idea of what was going on near to a point that you knew about, then you would need to use a linear approximation. Okay, I've got office hours now. If you can't come to office hours, you can ask me a question at the end, but if you can come to office hours, please go there instead. Okay, thanks very much, guys.